We are back together again, and we're continuing our adventures into applications of the derivative. New unit, but still derivative stuff. Today we're talking about the mean value theorem, and our learning objective for today is to identify and learn to justify the mean value theorem and Rolle's theorem. The mean value theorem. If f is continuous on a closed interval ab, and differentiable on the open interval AB, there exists a number C in AB such that f prime of C equals f of B minus f of A all over B minus A. What does that mean? Somewhere, the instantaneous rate of change equals the average rate of change. In other words, somewhere, the slope of the secant line equals the slope of a tangent line. Fun fact, some people consider the mean value theorem to be the most important theorem in calculus because it's used to prove so many other theorems. Example 1. Let f be the function given by x cubed minus 13x squared plus 44x minus 42. Find the number C that satisfies the conclusion of the mean value theorem for f on the interval 0, 8. What that's asking is, where is the point on the interval 0, 8 where the tangent line has the same slope as the secant line? That makes a little bit more sense to me. First of all, if we're going to use the mean value theorem, we have to state that f of x is continuous and differentiable. Now we can start doing some math. We need the point at the beginning, so that's f of 0 equals 42, and we need the point at the end of the interval, that's f of 8 equals negative 10. Now we can use those 2 points to find the slope of the secant line, f of 8 minus f of 0 over 8 minus 0. So f of 8 is negative 10, f of 0 is negative 42. We get a slope of 4. That's the slope of the secant line. Where does the tangent line have the same slope? Where is the instantaneous rate of change the same? Where is the derivative the same? So if the derivative is 3x squared minus 26x plus 44, we just set that equal to the slope of the secant line. Now we just have to solve for x. So subtract 4 from both sides, and then on the right we can factor. And now we can see that the instantaneous rate of change is 4 at 2 places, at x equals 2 and x equals 20 over 3. Rolle's theorem, pretty much the same thing, just more specific. Let f be continuous on the closed interval AB and differentiable on the open interval AB, and if, this is where the difference comes in, if f of A equals A of B, in other words, if it starts and ends at the same level, then there exists a number C such that f prime of C equals 0. So the slope of the tangent line equals the slope of the secant line, which is 0. In other words, if these conditions hold true, there's at least one place between A and B where there is a horizontal tangent line, because the graph has to turn around to get back where it started. So let f be the function given by x squared plus 2x minus 3. Find the number C that satisfies the conclusion of Rolle's theorem on the interval negative 3, 1. So I graphed it for you so you can see where we're going. And basically, we need to figure out where the graph turns around. First, in order to use Rolle's theorem, we have to say that f of x is continuous and differentiable. Then we need to find our endpoints. So f of negative 3 equals 0. and f of 1 equals 0, it's important that those are the same number. They don't necessarily have to be 0, they just have to match. So if the graph starts and ends at the same spot, then the slope of the secant line is 0. Now we need the derivative, that's 2x plus 2. Set that equal to 0 and solve for x. So at -1, and that checks out. A sports car speedometer registers 50 miles per hour as it passes a patrol car stationed at a mileage marker. 4 minutes later, the car passes another patrolman at a marker that's 5 miles from the first. The driver notes that the speedometer registers 55 miles an hour. Can the highway patrol use the mean value theorem to prove that the driver was exceeding the speed limit of 70 miles per hour sometime between those two mileage markers? Well, let's see what's going on here. We're going to call S of t a distance, and the car starts at distance 0, travels, and then the next mileage marker is here. That's 4 minutes later. So 4 minutes out of 60 minutes, we have a time hack of 1/15. So if our starting point is 0, 0, and 4 minutes later, he's gone 5 miles, we have 2 points. All right, well, let's find the slope between those points. So the slope of the secant line, 5 minus 0 over 1/15 minus 0, is 75. 75 miles an hour is his average speed, which means his instantaneous speed must have been 75 at some point. So that dude's getting a ticket. Example 4. Let h of x equal 5 minus 4x. Find all values of c in the open interval from 1 to 4 guaranteed by the mean value theorem. All right, so once again, where is the point on the interval 1, 4 where the tangent line has the same slope as the secant line? There's the secant line, and we've gone from 1, 1 to 4, 4. So the slope of that line is 1. Now if I take the derivative of h of x, I get 4 over x squared. I can do that over here if we need to. 5 minus 4 over x. That's 5 minus 4x to the -1. So the -1 comes forward, the 5 disappears, 4x to the -2. Okay, back to our problem. The instantaneous rate of change is 4 over x squared. I want that to match my average rate of change of 1. And now I can solve for x. So we have x equaling plus or minus 2. We don't care about the -2 because that's not on our interval, but we found a number c, which is 2, that satisfies the mean value theorem on 1, 4, and that checks out because at 2, the slope of the secant line matches the slope of the tangent line. Example 5, find all values between the x-intercepts for which Rolle's theorem holds for the roots of f of x equals 4x squared minus x to the 4th. First of all, can we use Rolle's theorem? We can, because f of x is continuous and differentiable, and because we're going between x-intercepts. So it's starting and ending in the same spot. And if we graph it, we can see that we're working through the x-intercepts. And what we're looking for is these places where the graph turns around. Where the graph turns around has a slope of 0. So we'll set the derivative equal to 0 and solve for x. Get a little bit more factoring practice here. And we have 3 spots, -√2, 0, and +√2. Last one, determine whether g of x equals sine 2x plus 2x satisfies the hypothesis of the mean value theorem on the interval 0, pi? If so, find all number c's in AB such that g of b minus g of a equals g prime of c times b minus a. There's so many letters. So let's start at the beginning. Determine whether the function satisfies the hypothesis of the mean value theorem. Okay, it does. Sine and polynomial functions, so we have a sine function and a polynomial function together, are continuous and differentiable. So we've got that. Now we need to find all numbers c such that this. That looks confusing to me, but if I divide both sides by b minus a, okay, this is what it looks like. That makes more sense to me because we have here the slope of the secant line, the average rate of change, and the slope of the tangent line, the instantaneous rate of change. So if our interval is between 0 and pi, we need g of pi minus g of 0 over pi minus 0, and then we'll set that equal to the derivative of g of x. So we have a chain rule here. Derivative of sine 2x is cosine 2x, and then times the derivative of 2x, which is 2. And then the derivative of 2x is 2. Now let's see, what is g of pi? So the sine of 2 pi minus 2 pi plus 2 pi. Sine of 2 pi is 0. So that's going to be 2 pi. And then g of 0, we've got sine of 0 plus 2 times 0 is 0. 2 pi minus 0 over pi minus 0 equals 2 cosine 2x plus 2. Now we have to solve that. So my pi's cancel out. 2 equals 2 cosine 2x plus 2. Subtract 2 from both sides. And then 0 equals cosine 2x. Well, where does cosine equal 0? Cosine equals 0 at pi over 2 and 3 pi over 2. So this angle, 2x, has to equal pi over 2 or 3 pi over 2. So if we divide both sides by 2, there we go. Pi over 4 and 3 pi over 4. There's the graph. So that checks out, pi over 4 and 3 pi over 4. Pretty nifty stuff. Hey, thanks for being here.